Black holes are terrifying objects that never let anything escape them. Anything that unfortunately passes too close to these giant space structures ends up deep in their bellies. Thankfully, black holes are so far away from the Earth that our planet is safe. However, some scientists have tried to recreate black holes in the lab. How did they manage to achieve this feat? Are they biting off more than we can chew? And should you be afraid of the lab-created black holes if things get out of hand? Join us as we bring you how scientists just brought black holes to the human planet. It is no secret that you should do your best to avoid black holes. They rip apart and swallow huge stars, spaceships, and even light. They are huge amounts of matter packed into tiny areas. Think of a star 10 times more massive than the Sun, squeezed into a sphere approximately the diameter of New York City. The result is a gravitational field so strong that nothing, not even light, can escape. But where do these monster objects come from, and how do they end up with so much gravitational force? You might be surprised that black holes in their former life gave off light by shining brightly. Most black holes form from the remnants of a giant star that dies in a supernova explosion. Smaller stars become dense neutron stars, which are not massive enough to trap light. If the star's total mass is large enough, like about 3 times the mass of the Sun, it can be proven theoretically that no force can keep the star from collapsing under the influence of gravity. However, as the star collapses, a strange thing occurs. As the surface of the star nears an imaginary surface called the event horizon, time on the star slows relative to the time kept by observers far away. When the surface reaches the event horizon, time stands still and the star can collapse no more. It is a frozen, collapsing object. The idea of an object in space so massive and dense that light could not escape it has been around for centuries. Most famously, black holes were predicted by Einstein's theory of general relativity. This theory showed that when a massive star dies, it leaves behind a small, dense remnant core. As the equation shows, if the core's mass is more than about 3 times the mass of the Sun, the force of gravity overwhelms all the other forces and produces the cosmic nightmare known as a black hole. You can't even directly observe black holes with telescopes that detect X-rays, light, or other forms of electromagnetic radiation. In fact, good luck seeing a black hole before it's too late when you are wandering in deep space. We can, however, infer the presence of black holes and study them by detecting their effect on the matter nearby. For instance, if a black hole passes through a cloud of interstellar matter, it will draw matter inward in a process known as accretion, and you could conclude there has been an encounter with a black hole. The same is true if a regular star unfortunately passes close to a black hole. In this case, the black hole can tear the star apart as it pulls it toward itself. As the attracted matter accelerates and heats up, it emits X-rays that radiate into space. Recent discoveries offer some tantalizing evidence that black holes dramatically influence the neighborhoods around them by emitting powerful gamma-ray bursts. However, black holes not only devour nearby stars but also spur the growth of new stars in some areas, although it is not above stalling the growth of others. One of the mysteries of black holes is how they can exist on 2 radically different size scales. For instance, you can have black holes that are the remnants of massive stars. In fact, there are countless numbers of such black holes in the universe. These stellar mass black holes are generally 10 to 24 times as massive as the Sun. Astronomers spot them when another star draws near enough for some of the matter surrounding it to be snared by the black hole's gravity, churning out X-rays in the process. Going by the number of stars large enough to produce such black holes, there could be as many as 10 million to 1 billion such black holes in the Milky Way alone. However, on the other end of the size spectrum are the giants known as supermassive black holes, which are millions, if not billions of times as massive as the Sun. Astronomers believe that supermassive black holes lie at the center of virtually all galaxies, even our own Milky Way, known as the Sagittarius A star. Scientists, though, are not content to study black holes so far away. Despite that these objects are extremely scary, these scientists are creating black holes in their labs right in our backyards. In 2005, the idea was put forward that an experiment here on Earth regularly creates objects that bear a striking resemblance to actual black holes, albeit tiny ones. Horatio Nastase of Brown University in Providence, Rhode Island, thinks that the intense fireballs created in an atom-smashing experiment at the Brookhaven National Laboratory in New York have remarkable similarities to the celestial phenomena. Professor Nastase's work was admittedly theoretical, and the amount of matter involved in typical particle accelerator experiments was relatively small, but a black hole is still a black hole. The relativistic heavy ion collider at Brookhaven threw the nuclei of large atoms such as gold together at close to the speed of light. The ensuing collision created enough heat to produce a plasma 300 million times hotter than the surface of the Sun. For a moment, the nuclei broke down into their constituent bits or particles called quarks and gluons, a state of matter that had not existed since a microsecond after the Big Bang that began the universe. Analyzing this process usually involves some horribly complicated quantum physics, but Professor Nastase decided instead to try a different tack and use string theory. He showed that the fireball's core had some of the characteristics of a black hole. The fireball was absorbing 10 times more particles than any quantum physics calculations could predict. He said that the particles were disappearing into the fireball before coming back out as thermal radiation, rather like real black holes suck in matter from around them and re-emit Hawking radiation. Much later, a group of Israeli scientists decided to test Stephen Hawking's theories about black holes. They were attached to the Technion, Israel Institute of Technology. They were trying to confirm two of Hawking's most important predictions, that Hawking radiation arises from nothing and does not change in intensity over time, meaning it's stationary. A co-author of the study, Associate Professor of Physics Jeff Steinhauer, said a black hole is supposed to radiate like a black body, essentially a warm object that emits constant infrared radiation. Hawking suggested that black holes are just like regular stars, which release a certain type of radiation all the time, constantly. That was what they wanted to confirm in their study. The black hole that researchers made in the lab was made of a flowing gas of approximately 8,000 rubidium atoms. They were cooled to nearly absolute zero and held in place by a laser beam. They created a mysterious state of matter known as Bose-Einstein condensate, or BEC, which allows thousands of atoms to act together in unison as though they were a single atom. The scientists used another laser beam to create a cliff of potential energy, which caused the gas to flow like water rushing down a waterfall, creating an event horizon where one half of the gas was flowing faster than the speed of sound, the other half slower. In this experiment, the team was looking for pairs of phonons or quantum sound waves instead of pairs of photons spontaneously forming in the gas. A phonon on the slower half could travel against the gas flow away from the cliff, while the phonon on the faster half became trapped by the speed of the supersonic flowing gas, as Steinhauer explained. It was like trying to swim against a quicker current than you can swim, which mirrors being in a black hole because it is impossible to reach the horizon once you are inside. Once they found these phonon pairs, the researchers had to confirm whether they correlated and whether the Hawking radiation remained constant over time. That process was tricky because every time they took a picture of their black hole, it was destroyed by the heat created in the process. This made the team repeat the experiment 97,000 times. They gathered more than 124 days of continuous measurements to find the correlations. They were so happy that their effort paid off because they showed that the Hawking radiation was stationary, meaning it didn't change with time, just like the late physicists predicted. Another group of scientists at the Max Planck Institute for Astrophysics in Germany became the first to combine the physical effects of Einstein's general theory of relativity with realistic stellar density models. They used a simulation that included virtual stars ranging from about 1/10 to 10 times the Sun's mass. The virtual stars skirted a black hole 1 million times the mass of the Sun in the simulations made with supercomputers. As they approach, all are stretched and deformed by the black hole's gravity. Some are entirely pulled apart into a long gas stream, a cataclysmic phenomenon called a tidal disruption event. Others are only partially disrupted, retaining some of their mass and returning to their regular shapes after their horrific encounters. The researchers discovered that it wasn't the mass determining which stars survive. Instead, their survival depends more on their densities. The team also investigated how other characteristics, such as different black hole masses and stellar close approaches, affect tidal disruption events. Let's hear what you think of black holes in scientific labs in the comments section below.